Hello, my name is Tommy Hefner, and today I will present our paper on privacy-preserving planning in stochastic environments. The main contribution of the paper is the extension of collaborative privacy-preserving planning, or CPPP, to stochastic environments. We achieved this extension by formulating a new algorithm to solve stochastic privacy-preserving problems. We also propose an improvement on this algorithm. To test our two algorithms, we have modified benchmark privacy-preserving problems to stochastic environments. Let's look at an example privacy-preserving planning problem. Here we can see a logistics problem. The agents are trucks, and they can move packages between cities and logistics centers, like G&H. We can see that each truck has a different zone where it can operate, and collaboration is required to move P1 from A to C. Let's say each zone belongs to a different trucking company. These companies might be competing, in which case they would not want to share some information to other companies while collaborating. For example, they might not wish to share the location of trucks. This information is considered private, and each truck only knows its own location. The public information is only the location of the packages. The goal of collaborative privacy-preserving planning is to plan the best strategy to get from an initial state to the goal state without exposing the information defined as private. Current privacy-preserving problems use deterministic actions, but in the real world, actions are much more stochastic. In order to solve domains with stochastic effects, we define Stochastic Collaborative Privacy-Preserving Planning, or SCPPP, as follows. A tuple, where the main difference from classical CPPP is in the existence of a transition function, giving us the probability of reaching one state from another state by performing an action. The definition is similar to that of an MDP, but it supports an arbitrary number of agents, K, and the state space is derived from all possible truth assignments to the set of propositions P. Zooming in on our logistics problem, the state here is comprised of the public truth assignment to the proposition of P1 at A and the private truth assignment to T1 at A and T2 at G. From T1's perspective, the state would look like this. T1 knows its own location and cannot see the location of T2, only an index which T2 can then translate to the actual information. The sets of actions could look something like this, and since actions have stochastic effects, T2 driving from G to D might result in reaching B with a probability of 0.2 or arriving in D with a probability of 0.8. Now that we understand what an SCPPP problem looks like, let's dive into how we can solve it. Our algorithm is called Distributed Real-Time Dynamic Programming, and as the name suggests, it is based on the RTDP algorithm for solving MDPs. Like RTDP, we run simulated trajectories through the state space. Unlike RTDP, we have multiple agents where one agent advances the trajectory each step. Let's look at the algorithm for agent I. We initialize the Q values for each state action pair to 0, as well as the value of each state. As with RTDP, our DRTDP is an anytime algorithm, and we can let the main loop of the algorithm run for as long as we want, stopping the algorithm when the current solution satisfies our requirements. First, the agent will check if it has messages from other agents and handle them according to the message type. If there are no messages, the agent moves on to advance the current trajectory. The agent selects the optimal action according to the current Q values. Here, for example, it will be load. Then the agent performs a Bellman update, samples the next state from the transition distribution, and then the next agent to advance the trajectory is selected. Now we will dive into these steps. In order to perform a Bellman update, the q-values of the reachable states from S by performing action A are required. Since it's possible for T1 and T2 to act in some states, T1's q-values might not be the best for each of the states. For this reason, T1 requests the q-values of T2 for each of the possible next states and uses the best current q-value to perform the Bellman update. Once T2 answers, agent T1 can update the state's values. After a few iterations where we assume that agent T1 was the best agent to advance the trajectory, we reach a state where agent T2 is the best agent to act, so agent T1 sends a trajectory message to agent T2, and next iteration T1 will no longer advance the trajectory. From this point on, T2 will advance the trajectory until the goal is reached. And then, a new trajectory will start again from the initial state. The algorithm runs these simulated trajectories through the state space, using multiple agents and each time exploring different actions by different agents according to the current Q values. As with RTDP, when all states are visited infinitely often, the algorithm converges to the optimal policy. Notice there are a couple of steps we skipped when we followed the trajectory advancement. We always assumed that the agent that really is the best agent to act is the one doing the acting. But that is not the case when the algorithm starts. We initialize the Q values to 0, and before we know which agent is the best to act, we must explore the state space and update the Q values in order to learn which agent should act and what action should it take. This means that each step of trajectory advancement requires agents to share Q values and perhaps switch the agent responsible for advancing the trajectory. To improve DRTDP, we propose an algorithm called Public Synchronization RTDP, or PSRTdp, which is an approximation of DRTDP. What is the weakness of DRTDP? Well, as we've mentioned before, after each action taken by an agent, Q values must be shared and the agent advancing the trajectory might change. That means a lot of messages sent between the different agents. Is this behavior actually required? The main difference between DRTDP and PSRTdp is the fact that in PSRTdp we only request Q values or send trajectory messages when a public change was made to the current state. For example, agent T1 loading P1 would result in a public change, since P1 is no longer in city A. But T1 driving to center G would only change the private state of T1's location, so there is no need for messages to be passed between the agents. We can see this behavior is implemented in the algorithm by separating updates to local in case of a private action and normal DRTDP updates otherwise. A local update is a Bellman update which uses the current agent's Q values without requesting other agents' Q values. There is still a problem in what I presented. What happens if agent T1 loads P1 onto the truck, and this being a public change in the state, sends a message to T2 and passes the trajectory for it to advance? T2 can only drive back and forth between G and B. No public change could ever happen from this point on. The private cycle detection mechanism, we can see here, aims to solve this issue by restarting the trajectory from the initial state. This is a delicate matter. If the cycle detection is too sensitive, it might trigger too many restarts caused by innocent exploration of the state space. If the cycle detection is not sensitive enough, we might waste precious time in a private loop. Choosing the sensitivity of the cycle detection mechanism is domain dependent and was set accordingly. Now to the experiments. The algorithms were implemented in Python. We ran experiments on 3 benchmark privacy-preserving domains, modified to have stochastic effects. every 10 RTDP trajectories, we ran an evaluation of the current policy using 50 simulations of agents acting in the space. The algorithm was terminated when evaluation cost converged. Let's move on to the results. Here we can see the results of DRTDP compared to PSRTdp on two problems from each domain. On the left are the results for DRTDP, and on the right PSRTdp. As we can see, the amount of messages passed between the agents in the planning stage was significantly reduced in PSRTdp compared to DRTDP. This also correlates with a reduced runtime of the algorithm, as we can see here. We can see that block swirl problems had small reduction in runtime in PSRTdp. A reason for that could be the fact that there is little private information in this domain. On the other hand, logistics problems, which have much more private information, had significant reduction in runtime in PSRTdp. In general, we can see that the greater the reduction in the amount of messages, the greater the reduction in the planning runtime. So let's conclude. We talked about the extension of collaborative privacy-preserving planning to stochastic environments and the DRTDP algorithm we formulated to solve such problems. We then proposed an improvement to DRTDP, called PSRTdp, and examined the differences between them. In the future, we would like to have agents advance multiple trajectories simultaneously, meaning while one agent advances a trajectory, another agent can advance a different trajectory. We also would like to explore concurrent execution of policy and its effect on the algorithms we've presented. Thank you very much for listening.